As a reminder, what we had accomplished last time was the sampling theorem for band-limited sequences. Which goes like the following. We assume that given xn is a finite energy sequence and it is band limited to some pi over m radians. Then we said that you take this sequence xn, you pass it through a filter, which is just a low-pass filter, and then you sample it every m samples, and you get back this x tilde dn. And if you take this x tilde dn and you then feed it to this expander, you low pass filter, and you get this x tilde in, then we are guaranteed that x tilde in is equal to x of n, as long as your x of n is band limited to pi over n radians. Now you can look at the same expressions again and find out that if xn was not band limited to pi m, then this would not hold. But if you go through this this flow of low pass filter, sample, then up sample and low pass filter again, what you can show is that this x tilde in, which has this Fourier transform x tilde I e to the j omega, you can show that this x tilde I e to the j omega is simply x of e to the j omega for omega less than or equal to pi over m, for omega in principal period minus pi to pi, and there is of course periodic repetition after that, and 0 otherwise. In other words, what this sampling expression for band limited sequences do is it first low pass filters the sequence to pi over m radians, and your output is simply the low pass filter version of that original sequence if it was not band limited to pi over m radians. If your sequence was band limited, then of course you get back the same thing. Okay. So this completes our discussion of sampling theorem for band limited sequences, which we derived using the subspace projection formula. But what we now want to do is take this discussion forward and look at all the individual components of sampling theorems, both continuous time and discrete time, in the frequency domain. Because if we have a digital system which is made up of different components, you have maybe a component which takes continuous time signal to discrete time. You have a component that does decimation of the discrete time sequence, filtering of sequences, and so forth. And at the end of the day, you reproduce a continuous time signal. Then if you understand what each of the blocks is doing in frequency domain, then you can write down the expression or the effect of this whole digital system on the frequency of the input signal. Okay. So our digital systems are made up of these different blocks: sampling of continuous time signals, decimations, upsampling, filters, and we need to be able to understand what does each of these blocks do in the frequency domain. Okay. So that is what this lecture and perhaps the next lecture will be about. We are done doing the basic expressions for sampling of continuous and discrete time sequences. We are now going to move forward towards the frequency domain interpretation of different components of these sampling operations. So the operations we have seen in the continuous time sampling, discrete time sampling, there are two main types of operations. There is filtering operation, and there are these sampling operations or conversion from sequence to an impulse train, or this decimation or upsampling. So let's look at, of course, the filtering operation. So we are given a signal and we do filtering of that. Now the input could be continuous time or it could be discrete time. So x of t or x of n. At the output we get y of n or y of t. As long as the filtering operation, this block is LTI, we exactly know how the inputs and outputs are related. So if we say that the filter is given by, in discrete time it is hn, which has h of e to the j omega, and in continuous time it is ht, which is h of j omega, we know exactly how they affect the output. So in the discrete time, in frequency, the output is simply multiplication of your dTft of the input times the frequency response of your filter. Similarly, in continuous time, we have a similar expression. The output frequencies are simply the product of the input frequencies and the frequency response of your filter. This means that at least as far as this filtering component of our digital systems is concerned, we already know from our previous knowledge what happens between the frequencies of the input signals and the output signals. So we are not going to spend time on learning about that. What we need to think about is about the other components in our digital systems. So since we were talking about discrete time systems, let's continue our discussion of those. So one of the components we studied was this decimation operation. You are given some sequence xn, you get xdn. So let's understand what does this decimation operation do in the frequency domain. The analog of that in the continuous domain is that we got x of t, we multiply it with an impulse train s of t, so summation delta of t minus nt, and we get back xs of t. And if you remember, we were able to show that this xsj omega, that is simply given by scaling of your amplitude and multiple copies of the Fourier transform of your input signal. It's given by xj omega minus 2 pi k over t. And we are looking for some sort of a similar expression in the discrete time case. So the question we are asking is, if this thing has a Fourier transform xn, x of e to the j omega, and this thing has a Fourier transform of xd of e to the j omega, what is the relationship between these two if you pass them through this decimation operation? That is going to be our first goal. Now to do that, we have to again do the same trick as we did in the continuous time, which is we try to express this operation as multiplication with some sort of an impulse train. So remember the definition of decimation, which is xd of n is given by xn of m for n equals 0, plus minus 1, plus minus 2, and so forth. So my goal is I'm looking at this xdn, which is given by every m samples of my original signal xn. Okay? And I'm going to express this as multiplication with an impulse train. So whether I write this as xdn equal to xnm, or I multiply my x of n with s of n, where s of n is an impulse train. So x of n times k minus infinity to infinity delta of n minus km. And I now subsample this thing. So I say that I subsample this thing every m samples to get back xdn. The claim is that both of these operations are the same. So why? Because what is xdn doing? It is collecting, it is keeping the mth sample and throwing away every m minus 1 samples. Okay. Now what is this thing? This is just an impulse train which is non-zero at multiples of m and 0 everywhere else. To m minus m. Now whether I first downsample my xn directly or I multiply my xn with this train, which is going to actually make all my samples between 0 and m 0, and then downsample, it's going to be the same operation, because the values that I'm going to make 0 in xn, those values I was not going to keep anyways. Okay. If I take x of n, okay, and I downsample that, I get xdn. Okay. Whether I do that or I take x of n, I multiply that with s of n to get xn Sn, which is this thing. Okay, and I downsample them to get xdn. They are both same. We are originally interested in this upper block diagram. Okay, our output is every m samples of xn. But what I want to do is understand what is the frequency relation of xdn to xn. To understand that, I'm going to reduce this block diagram into a further two-step process, where I first take my xn and I multiply that with an impulse train. What is this impulse train doing? It's making all entries 0 except at 0, m, 2m, and so forth. And then I downsample by factor of m. At the end of the day, whether I first make the entries in between 0 and then throw them away, or I throw them away directly, my output is the same. Okay? But the reason we are doing this is because it will help us analyze the frequency transform of xdn in terms of the frequency transform of xn more easily. That's the essence of this operation, dividing this one-step procedure into two steps. So what we, instead of xdn equals to x and m, what we are going to look at is x dn equal to x and m and s and m. And we are going to compute the DTFT of this expression. Now, I defined Sn to be this periodic impulse train, delta of n minus km. I can also write that as this exponential summation. The way to see that is simply use your geometric sum formula. So if my n equals to a multiple of capital M, okay, if my n equals to multiple of capital M, so Km, then what happens to this exponential? It becomes e to the j times an integer, 2 pi times an integer, which means it becomes 1. And there are m terms in this, so the sum of that is m, and I get 1 over m. So in that case, I just get 1. Okay? But if n is not equal to some multiple of m, then you can use the geometric sum expression. Okay? 1 minus ratio to the total number of terms divided by 1 minus ratio. And the numerator of that will be 0 in that case. So you get 0. So I've just written this periodic summation in this exponential form. It's the same thing. Okay. Now I'm going to ask to compute the Fourier transform of my x dn, which is simply x dn e to the minus j omega n from minus infinity to infinity. And I just put in the values of x dn, which is x and m, s and m, e to the minus j omega n. Okay. Now I can simply do a change of variables, and I replace this nm, so put n equals to L over m. Because of the fact that this is over all indices, I can do that, because even when it becomes XL, SL, this whole thing stays the same. So I get L minus infinity to infinity, X of L, S of L, e to the minus j omega L over m. Okay. Now I am simply going to replace this value of SL using this formula. So I get summation over L, X of n, 1 over m, summation m equals 0 to n, m minus 1, e to the j 2 pi m L over m, and e to the minus j omega L over m. So I'll just replace this SL with its formula. Now I'm just going to do a change of summation order. So I'll just bring this summation over m outside and take the summation over L inside. So I'll get 1 over m, summation of m equals 0 to m minus 1. The other summation is L equal to 0, L from minus infinity to infinity, X of L, e to the j 2 pi ml over m times e to the minus j omega l over m. Okay. So that is 1 over m, again summation over m, 0 to m minus 1, summation over l, xl, and I'm going to put both of these exponentials together, so I get e to the minus j omega minus 2 pi m l over capital M. Now, just to remind ourselves, we are computing xd e to the j omega. Now let's look at this expression inside the first summation. Okay. What is this expression? This expression is simply equal to x of n e to the minus j omega n with omega replaced by omega minus 2 pi m over capital M. In other words, this is just the dtft of xn, where I have, instead of omega, I have omega minus 2 pi m over capital M. So this whole expression is simply x of e to the j omega minus 2 pi m over capital M. Which means that the Fourier transform of my decimated signal is simply 1 over m summation of m equals 0 to m minus 1 x of e to the j omega minus 2 pi m over capital M. Okay. So that is the relationship between the input and the output of a decimator. What is the relationship saying? That first of all, your output frequencies are simply given by your input frequencies, which are just scaled by some factors. So there is first an amplitude scaling by a factor of 1 over m. If you remind yourselves of what happens when you look at the frequency of xst, there was a factor of 1 over t there. It's very similar in the discrete time. There is a factor of 1 over m. If you look at this, you have scaling of your frequency axis by a factor of, so this thing is doing frequency axis scaling by m. Now in the continuous time world, you got multiple copies which were shifted by 2 pi k over t. In the discrete world, we get multiple copies which are just shifted by 2 pi m over m, or simply 2 pi m if you just first do the scaling. The only main difference is that instead of an infinite summation, you have a finite summation. You have an m-fold, m number of copies. The reason for that is that in the continuous time world, actually, you wanted to get infinite number of copies. In the discrete world, you are already starting with this periodic Fourier transform, right? So you don't really need infinite number of copies. You just scale them and you put m copies together and you add them all up and you get back the Fourier transform of the new signal, of the decimated signal. Okay. The main thing that happens in the case of decimation then is the following. Decimation does three main things. Number one, xd of e to the j omega has amplitude scaling by 1 over m. Okay. That is very analogous to the continuous time case. The other thing which is the more sort of difference from the continuous time world is that you would get m copies of the DTFT instead of infinite copies in the continuous time. And the third is that each copy is, number one, scaled in frequency by a factor of m, and then number two, shifted by an amount of 2 pi m. So decimation does these three things. It scales your amplitude, it gives you multiple copies, m number of copies, and each copy is given by just a scaling of your frequency axis by m and shifting by 2 pi m. Okay. So let's take a look at an example to give you a better sense of what happens. So let's say that you are given an xn, which has xe to the, whose Fourier transform is xe to the j omega. You decimate it by a factor of 2. And we get xdn, which is given by xd of e to the j omega in its Fourier transform. So let's look at what does this do. Assuming that xe to the j omega is given by the following. So let's take our usual diagram of just a rectangular region. And I will, so this is my 0, my 2 pi, 3 pi, 4 pi. So this is 0, 2 pi, 4 pi, similarly minus 2 pi, and minus 4 pi. Minus 2 pi, these are, this is pi, here is 3 pi, minus pi, minus 3 pi. So to compute, we need to first of all look at two copies of this same Fourier transform. Okay, each copy's amplitude is scaled by 1/2. So I have one replica 1, which is simply x of e to the j omega minus 2 pi 0, which is 0 over 2. Okay. So what would that replica look like? I'm going to change my color here. So let's go here. First of all, your amplitude, if this amplitude was, let's say, a, this will become a over 2. Okay. Now the endpoints, let's assume that these endpoints, for concreteness sake, were at pi by 3 and minus pi by 3. This whole thing, this frequency axis is getting multiplied by a factor of 2. Things are being stretched. So this pi by 3 frequency moves to 2 pi by 3. So what I end up getting is a number which is here and here. This is going to be 2 pi by 3 and minus 2 pi by 3. Now this 2 pi copy, this 2 pi version this gets multiplied by 2 and it ends up being at 4 pi. Okay? So then, so this one of course comes down and this one will move to 4 pi. You have a stretching of your frequency axis. So this thing will move to 4 pi with a height of a over 2. Similarly, this copy will move to minus 4 pi, again minus 2 pi times 2. And with a height of a by 2 and minus 4 pi. So this first replica has nothing between minus 4 pi and 0. Okay. Now the second replica, replica 2, which is given by x of e to the j omega minus 2 pi over 2. That replica you can actually start from replica 1, because what is this thing saying? That it is the same as this one, which is, I should have a 1 over m factor since I'm reducing the height by factor of 2, so there is a 1 over m factor here. So to figure out what will this replica look like, you just look at the above one and shift it by a factor of 2 pi. So which means that this copy will actually move to 2 pi with a height of a by 2. This is 2 pi. And this copy is going to move to, so this is moving to 2 pi. This 4 pi is moving to minus 2 pi. And there is, of course, nothing at 0 or 4 pi and minus 4 pi. So these are the two replicas, and to get to the final Fourier transform, we just add them all, both of them up. And if I add both these replicas up, what I get back is I get a copy here due to the red copy, and here with the height of a by 2, and these things become 2 pi by 3. And then, and of course, a copy here, a by 2. And then due to this blue thing, I also get copies at minus 2 pi and 2 pi, which look like this. Okay. So another way you could have actually just thought of this Fourier transform is that you just look at your original Fourier transform and you just stretch the whole thing by a factor of m and scale the amplitude by a factor of 1 over m. Okay? That's another indirect way of thinking about it, because everything is periodic. Remember, in Fourier transform, if you know what are the things between minus pi and pi in the discrete time world, you can just replicate them, because discrete time Fourier transform is periodic. So, but this is what the meaning of the multiple copies is. One copy gives you values at 0, 4 pi, and then it will go to 4 pi, will move to 8 pi, and so forth. The other copy will sort of fill in the holes for 2 pi, minus 2 pi, and so forth. And then you add them all up and you get this all filled up Fourier transform, in which the main thing that has happened is your amplitude has scaled by a factor of 1 over m, and your axes have stretched, your frequency axes have stretched by a factor of m. So if you had a frequency which was in the previous sequence, let's say the frequency was available at 0.1 radians, the new frequency will, that same frequency will appear in the decimated signal at 0.1 times m. Okay. So that's the effect of decimation that on the discrete sequences. It doesn't matter whether the sequence comes from continuous time or not. If you are given a discrete sequence and you decimate it, the frequencies primarily move to another location, which is given by scaling by a factor of m. In this example, we had taken the case purposefully of x e to the j omega being band limited to pi by 3 radians. So when we scaled the frequencies, they went to 2 pi by 3. Okay. Let's ask the question, what happens if it was actually band limited to another number such that when I scale, the scaling goes beyond pi? So let's assume that we had a signal which was band limited to actually 3 pi by 2 radians. So assume that you are given x of e to the j omega band limited to 3 pi by 4 radians. What happens if I now take that sequence and I decimate it by a factor of 2? The effect that we get is very similar to the effect of aliasing that we saw in the continuous time world. We are looking at multiple copies, and each copy is now being stretched. So instead of drawing both the copies and then adding them up, I'm just going to go to the shorthand. If my original sequence was like this was its Fourier transform. This is 3 pi by 4 minus 3 pi by 4. This is minus pi, pi. And of course, you have the same thing at 2 pi and minus 2 pi. So if this is my x of e to the j omega, and I do decimation by a factor of 2, let's say again the height is a, denoted by a. If I do decimation by a factor of 2, let's just look at the main copy and then we'll just replicate that everywhere else. So what happens to the main copy? The height gets scaled by 1 over m, so it will become a by 2. Okay. So this height will a by 2. But these endpoints, they will be scaled by a factor of 2. So these endpoints will go to 3 pi by 4 times 2. That will go to 3 pi by 2. Which means that these endpoints will go beyond pi. So if this is your pi, your endpoint will actually end up going here. 3 pi by 2. Similarly, this is minus pi, and your endpoint will go beyond that, minus 3 pi by 2. Okay. And now you are going to do the same with all the other copies. So if I look here, I'll have the same thing happening. This thing will go beyond pi 2. Similarly, this thing at minus 2 pi will go beyond pi. And my Fourier transform of my decimated signal will effectively is going to be the sum of these. So up to this point, I get the same. But here, I now add the 2 copies up. And then I get this. Similarly, I get up to this point, this. Then I add the 2 copies up, and so forth. So what is happening is that in the discrete world, of course, frequencies near pi are the high frequencies. I am having the same kind of relationship that these frequencies are after pi are just folding down into the lower region, and they are corrupting your other frequencies. they are aliasing into lower frequencies. They are assuming identity of different frequencies. And that helps you explain also what is the purpose of the pre-filter in the discrete sequence sampling that we studied. The band-limited sequence, if you remember, we said the assumption is that you actually always cut off at pi by m, and then you do decimation by a factor of m. And you can see what this filter, low-pass filter, is doing when we are doing downsampling or decimation. This filter is exactly doing the same as we saw in the continuous time world. It is doing anti-aliasing. It is going to cut off everything that is above pi by m. If indeed we had a filter which was going to limit pi by 2, we could have a filter which was going to limit everything by pi by 2, and then we would not have this aliasing. Okay? So the essence is the pre-filter in the discrete sequence sampling, its role is similar to the continuous time world. It is doing anti-aliasing. And if you look at decimation operation without that filter, the effect of that is simply that your amplitude gets scaled by a factor of 1 over m, and your frequency axis gets scaled by a factor of m. That's the basic operation that is happening in the frequency domain when you do decimation. So we have finished discussing the effect of decimation on the frequency of the input signal. Decimation is a very basic operation that we do in the discrete world, and since we understand what it does in the frequency domain, we have a pretty good handle on how to make sure our decimation doesn't lose information. Okay? One of the key things for us not to lose information through decimation is that we must not let aliasing happen. So our decimation factor, m, should be in relation to the frequency content of my input signal. Let's now look at what does the expander do. So the question is, what is the effect of expansion on the frequency content of x of n? That actually is a much simpler thing to evaluate than the decimation part. So if you remember the expander, which notation being this up arrow with a factor of m, x, e, n, that is simply given by you take your sequence and then between any two samples insert m minus 1 zeros. Or stated differently, that is simply equal to k minus infinity to infinity x of k delta of n minus km. So I can compute the Fourier transform of this thing. It is x e to the e j omega. So I have summation over n, and then summation over k, x of k, delta of n minus km, e to the minus j omega n. Now, I'll just change the order of summation. I'll take the summation over k outside, and I'll take x of k outside too, and inside I'll have summation over n delta of n minus km e to the minus j omega n. And I'm going to look at this expression. Now, this thing is simply delta of n minus km e to the minus j omega n, that is equal to e to the minus j omega km. So this whole summation is just given by e to the minus j omega km. Simple evaluation, and if we put that in, we get kx of k e to the minus j omega km. So let's look at this thing. This is nothing but, if I just compute x of n e to the minus j omega n and replace omega with omega m, then this is the same thing. Of course, k or n, they are dummy variables, so they don't matter. So what is this thing? This thing is simply x of e to the j omega m. This is the Fourier transform of my x, and this thing is effectively saying that x of e, the expansion sequence, its Fourier transform, is given by a simple scaling of the frequency axis of your original Fourier transform. Okay? The end expression that we are getting is that x of e to the j omega is simply equal to x e to the j omega m. Okay. No multiple copies, no scaling of amplitude, just a pure scaling of the frequency axis by a factor of 1 over m. So if we take an input sequence and we just add zeros in between, all that happens is our frequencies get scaled by a factor of 1 over m. If you had a frequency at pi by 2, it starts appearing at pi over 2m. Okay? So while decimation did a stretching of the frequency axis, your frequencies get multiplied by m. Expansion does a compression of your frequency axis. So it's expansion in time, but it is compressing the frequency axis. Frequencies get multiplied by 1 over m. Okay? The usual duality experience that we have, that if you do something in time, in frequency, the sort of opposite of that happens. We are doing expansion in time, we end up compressing in frequency. So we can say that expansion, the effect of that is simply the dTft of the expander of the expanded sequence xe of n is simply given by the dTft of x of n with frequency axis scaled by 1 over m. So if I am given, for example, just take again the usual picture. If I am given a Fourier transform x of e to the j omega, and let's say it is up to minus pi and pi, okay? 2 pi minus 2 pi. Well, there is no amplitude scaling at all. Nothing happens in the amplitude. What happens is scaling of the frequency axis. So you get this pi moves to pi over m. this 2 pi copy moves to 2 pi over m. And that keeps on going till you hit pi. So originally you have only one copy of your sort of main signal between minus pi and pi. By doing this compression within minus pi and pi, you are actually going to get more than one copies. You are going to get m minus 1 copies because you are sort of compressing things inward. Okay, so if you want to understand that better, let's relate actually to the special case of m equal to 2 just to concretely see that. So for m equal to 2, this will become minus pi by 2 and pi by 2. And this copy, of course, will move to pi. And we'll get this. And this copy will move to pi. So we'll get this copy and this copy. So this version, this triangle is coming from this side, from 2 pi. And this triangle is coming from minus 2 pi. Okay, so between minus pi and pi, previously I had just saw one triangle, and now between minus pi and pi, I'm getting this whole thing. Okay. Now, if you remember for reconstruction, what do we do in the case of band-limited signals? For reconstruction, in the case of band-limited signals, we say, you are given some xdn, you first do expansion by a factor of m, and then you do low-pass filter with a cutoff of omega c equals to pi over m. Okay. So effectively, what this filter, in the case of band-limited signals, our filter was given by sinc. Sinc is a low-pass filter. The cutoff for that was pi over m. What this is doing is effectively, since you have compressed the frequencies, there are now frequencies which did not really belong to the original signal, right? This cutoff basically gets rid of this copy and this copy, or this side of the copy and this side of the copy, right? If this whole thing was in conjunction with a sampling system, you are doing reconstruction. You first had expansion, and then you are doing this cutoff. So that sort of is another way of looking at why do we need the cutoff filter at the end of expansion. Expansion alone is not enough. Right? Or you can think of that the cutoff is just interpolating the non-zero values. There are multiple ways of thinking about the post filter. But in general, the main goal that we were after is figure out what does the expansion do in frequency, just this block. What does this block alone do in frequency? And we saw that that block simply compresses the frequencies by doing scaling of the frequency axis by a factor of 1 over m. Okay. So they are complementary to each other. If you do decimation, your frequency axis gets scaled by a factor of m. You get multiple copies. You can think of those multiple copies in whichever way you want. But you can also just think of the principal period between minus pi and stretch that. In expansion, opposite of that happens. Your frequency axis gets scaled by a factor of 1 over m. The main difference between the two is that there is a scaling of the amplitude also in decimation. In expansion, there is no scaling of the amplitude. If we are given now digital systems which are doing sampling of discrete sequences using decimation, or they are doing expansion, or they are doing filtering, from end to end we can write down what happens to the frequencies. Okay. It's not too difficult to go through each step separately and figure out. For example, if you are given a sequence xn and someone says there is first an upsampling, then there is some filter. I'm not going to say what the filter is doing. It's h1 e to the j omega. Then there is some downsampling. Then perhaps another, and these factors don't have to be same, m1 and m2. Then there is an upsampling by a factor of m3 and another filtering, and the output is yn. Well, it's very easy to figure out what is the output, because you can go from, in the frequency domain, you can go from here to here. You know what happens. So you go from here to here, you know what happens to the frequencies. A scaling of the axis. You go from here to here, you know what happens to the frequencies. Simply multiplication with the frequency response. You then go from here to here. Again, you have scaling of the axis and amplitude scaling. Then you come from here to here, the same thing. And finally, another multiplication with the frequency response. So no matter what kind of a digital system you are given, their blocks are going to be only either upsampling, downsampling, or filtering. If that's the case, then you can easily write end-to-end expressions. Okay. So there is nothing more for us left to be done in terms of understanding the frequency aspects of these blocks in discrete time. There is only the remaining thing that is left for us is actually understanding a couple of blocks in the continuous time and understanding a couple of identities in multi-rate signal processing, which actually are very useful in terms of, if you are given, let's say, a downsampling operation where you are required to first do anti-aliasing and then do downsampling. Okay. So let's say you are given a system where you are supposed to do downsampling by a factor of, let's say, pi by 16, and cutoff frequency of pi by 16, low-pass filter, and then you downsample by a factor of 16. If you think about it, this filter has a very small bandwidth, and building these filters, if you have seen any filter building literature in your undergraduate level, building these filters with small bandwidth can be pretty hard, or it can consume a lot of resources. Okay. It turns out that actually you can replace this with a 2-stage or even a 4-stage downsampling, where each filter is no more than maybe pi by 4 cutoff or pi by 2 cutoff. Okay. That goes back to two fundamental identities in multi-rate signal processing, which let you change the order of downsampling or decimation and filtering, so that the final input-output relation doesn't change. Okay. So we will see that actually this very same expression can be implemented by having filters which cut off at, let's say, pi by 4. Then you downsample at 4. Then you have another filter with cutoff of pi by 4. And then you downsample by a factor of 4 again. And if you now think of it, you have to implement filters which have a larger bandwidth. They have a pi by 4 bandwidth rather than pi by 16 bandwidth, which might have been difficult to implement. So in the next class, we will go over these identities, and we'll look at the remaining 2 pieces in the continuous time sampling. Together, then we will be able to figure out, give any system, DSP system, it could have continuous time signals, discrete time signals. As long as these components are there, we understand what happens with input, output of each of the components. We can write down what will happen when you start from the very beginning and end at the very end by simply traversing each block in the frequency domain. Okay? That we'll do next time.